All right, so 1.2 limit of a function. We're starting off with this function right here, and I asked you to take a few minutes to tell me what you know about this function. What can you tell me? Okay, I had one answer already. It is a function. Very good. Thank you very much. This is a function, and what do you know about it? You know that it's a function. Very good. Okay, wonderful. I'm actually looking for something a little bit deeper, okay, a little bit more than that. So we had another option say, listen, x cannot equal, there are some restricted values. I love it. Okay. X cannot equal, I think that it was x cannot equal 4 and 1. So this is what, well, I gotta write it down here, okay? So this is what you told me that the reason why it can equal certain values. And then we kind of figured out that, you know what, that's actually not true. Why? Because we actually have factored this denominator incorrectly. How do you know that? Negative 4 plus 1 would be negative 3. Negative 4 times 1 would be negative 4. So that doesn't add up at all. If you had negative 1 and positive 4, would that help? Not really. 4 minus 1 is 3, but you remember, you got these mixed up here, okay? So it has to add to this number, multiply to this number. That's how you factor, okay? So just a little refresher course there. So how can we factor this? What is it? X minus 3. X plus 1? Minus 1. Yes, okay. All right. Okay. Calculus 30 students. You need to know how to factor, okay? This is super important, all right? You need to know how to factor. All right. Now, negative 3 times negative 1 is positive 3. So that matches that. Negative 3 plus negative 1 is negative 4. That matches to that term. So that is what we're looking for. Okay. So one of the things that you can tell me about this is that x cannot equal what? Positive 3 and positive 1. Okay? Thank you. Very good. Anything else that you know about this function? Slant? Slant what? There's a slant something? It's a slant function. There's a slant line. Okay. A slant asymptote? Yeah. A slant, yeah, maybe? Okay. Let's see. I gotta write that down. Slant. You said slant something. Okay. Let's come back to that. All right. Slant something. Okay. Anybody else? Sorry. 3 is a point of discontinuity. Ooh. Anybody remember that from pre-calculus 30? Okay. So x equals 3 is a point. I'm gonna write it down. Point of discontinuity. A pod. Yes. Why? Why is that? Someone tell me. Look at that. The factor in the top and a factor in the bottom are the same. Exactly. And so this is a rational function. Nobody said that yet. It's a rational function. Okay. And when you can divide out a common factor like that, yes, we have a point of discontinuity. Okay. And I think maybe what you were thinking about, if we come back to slant, there is a vertical asymptote there. Okay? And so maybe that's what you're talking about, a vertical asymptote, and that's going to be at x equals 1. And there's a discontinuity at 3. Okay. All right, that's really good. That's really good. We're going to zero in on this particular fact right here. Okay? Point of discontinuity. I'm going to show you the graph here. So here's the graph for this rational function. So there is a vertical asymptote right here at x equals 1. That's one of our restricted values. It's a vertical asymptote. And notice back from the notes here from pre-calculus 30, if it does not get divided out and it's a restricted value and it's in the denominator, it's a vertical asymptote. If it's a restricted value in the denominator but does get divided out, that means it's a point of discontinuity. So if we look at that, a point of discontinuity. Now in this graph, it appears that x equals 3, it's going to be right there. It appears that we don't have a problem here. It looks like it's completely, it looks like there's not a discontinuity. But I don't know if you guys remember last year, I think we maybe did this in one of the classes. If you zoom in enough, because remember, a point is an infinitely small region. So if we zoom in enough, look what happens. Check it out. That's what a point of discontinuity looks like in Desmos here. As the x value comes this way and approaches x equals 3, notice the terminology I'm using, as x approaches 3 from either side, we are approaching a region here where there's a problem. And this is what happens. It's like, okay, as I get close to this restricted value, it kind of freaks out a little bit. And this would be, in our drawing, we would just draw a circle with a hole in it, right? That's the gap. Remember that? So we draw a hole right there. So that's an undefined right there. But notice that really, in the grand scheme of things, it is not a vertical asymptote. And it doesn't like me doing this. It's taking some time to think about it. So, okay, here we go. So in the grand scheme of things, this is not a vertical asymptote at all, is it? It's a gap discontinuity. A vertical asymptote would be at x equals 1 over here. Right here. That's right there. No, x equals... Oh yeah, I guess I zoomed in a little bit much. There we go. So x equals 1 right here. Okay, now if we think about this x equals 3, right, as I mentioned before, as x approaches 3 from both sides, what does the function actually approach? So what would the value be if x equals 3 happened to be defined here? So you're looking not at the point itself, but you're looking at everything around it, right? So as we zoom in here, again, it looks like the function should equal this value right here. And what is this value? It's about 0.5. Now it doesn't equal that, but it looks like the function kind of comes like this, right? And it approaches y equals 0.5. I think this can be, I have this right here. And this actually is, I think, simplifies things for us. As x approaches 3, the value of the function actually, whichever way we go, it kind of comes down here to x or y equals 0.5. See that? And as we move towards 3 from this direction, the y value, the function, actually approaches up to 0.5. So even though x equals 3 is not defined by the function, there is a limit. Okay? There is a value of the function if we take the limit of all of the values surrounding that x value. And so in this section, right, in 1.2, we're trying to explain what a limit of a function is. And so here we go. This is the function. If they calculate simply f of x values for x values leading up to 3, 2.5, the f of x value is 2/3. 2.9, it's this. 2.99, it's 5.502. 2.99999, right, it's not 3 yet, but look at how close the function value is to exactly 0.5 even. And of course, as we get closer, the value gets closer to 0.5. From the other direction, you see that it creeps up to 0.50. So in math, usually in math, we take an x value and we plug it into the function to find out what the y value is, right? That's what we usually do. When we're talking about limits, we don't start with the x value to calculate the y value. What we do is we look at all of the other x values leading up to, all of the other x values, and we look at all of the other y values leading up to, but we don't look at the actual x and y. It's not in the picture. It's not even there. So we don't even consider the x. We look at what happens around it. You see that? And so we can come to the conclusion that, hey, it would be the value for this function if it was defined. Make sense? Okay. Any questions? So what you could say here is you could say the limit of f of x as x approaches 3. Okay, so that's what you write underneath that limit there, lim, x, arrow, 3, as x approaches 3. And this whole limit here, this is 0.5. And once again, I just want to stress this once again, we are not saying that when you plug x into the x equals 3 into the function, you get 0.5, because you don't. But the limit of all of the other values tells us that at x equals 3, the value would be 0.5. Okay? Contrast that, okay? Contrast that. Let's use a different color. What's the limit? And just to let you know, I've written this limit a million times probably in my life. Actually, not quite, but it seems like it. And so it gets really messy. It is indiscernible. So if you see this, that means a limit, okay? And if you write it messy too, I won't I won't get after you. But as x approaches 1 for the function, what do you think the limit is? So x is approaching 1 here from both sides. What does the red graph seem to approach? Which y value? Does it seem to approach a value like this one, like 0.5 over here? Does it seem to kind of go, hey, you know what, look, we're all coming to this value right here. We're coming right here, this is the limit. Is there a limit? From the right side, look at this heads up to positive infinity. It goes out of control. Down to negative infinity. So guess what? This does not exist. Does not exist. The limit of the function, this function that's given, as x approaches 1, does not exist. dne does not exist. Okay? And that's good enough for now for you guys to say that. All right? Got it? This is kind of weird, isn't it? Kind of doesn't even really seem like math. But the concept of a limit is very, very important. Okay. Where are we going next? Oh, next section. Okay, don't want to do that yet. The textbook tells us this, okay? So here's where it shows you this limit notation. Okay, the limit as x approaches a of f of x equals L. L is the limit. A would be some value. So we substituted 3 in there and we substituted 1 in there, right? And it's read like this. The limit of f of x as x approaches a equals L, some limit. So if we make the values of f of x arbitrarily close to L as we like by taking x to be sufficiently close to a but not equal to a. So that is, I didn't say that at first because that seems a little bit wordy, doesn't it? And all that really means is that as your x value gets closer and closer, right here, to a, the function will get closer and closer to L, whatever that limit is. And it could exist, but it might not. Okay? If you have a gap discontinuity, then it's going to approach a limit there because on both sides the function is behaving. It looks like it's zeroing in on a point, right? Okay. As well in the textbook, just going to probably wrap things up here pretty soon. But as well in the textbook, they give you properties of limits. I'm going to revisit the properties of limits, but I will show them to you. You do not have to copy them out or anything. But on the next page here, I believe, properties of limits. Now, I'm going to revisit this a little bit later because this is just too much right now. I just find that it's just too much to go through this with students right now. We want to take it a little bits at a time. But limits have properties just like there's properties of integer properties, there's exponent laws, there's properties of logarithms and stuff like that you study. So there's certain things we can do with the limits as well, but that's going to come a little bit later. Please don't worry about that. All right. You guys okay so far? Is it a bit warm in here? All right. It is a bit warm, I'm sorry. Okay. Now this is using properties of limits. Okay, let's take a look at example 2 here. Okay? I'm going to clip this out and I'm going to just kind of show you what you would do. Come hither. Okay, see what that looks like. Blue. Okay. Dark blue. Darker blue. You guys like the blue background or no? I don't know. Not decided on the blue background. Yes, you like it? Better than white? Alright, well, we'll see. Okay, so what happens if you get a question like this? Okay? Now, this is not a rational function, so there's no restrictions on this. Okay? So basically, this is kind of a trick question, but it's not. All this is trying to say to you is that, listen, even if it's a continuous function like this thing is, and this is some parabola, right? Even if it's a continuous function, you can calculate a limit because the actual value of this function right here, when you plug x equals 5 in, a lot of times that is the limit. Right? A lot of times that is the limit. So it doesn't have to be a gap. It doesn't have to be something special. It can be just a regular continuous function. And in these terms, what's the limit as x approaches 5? Well, it could be just whatever the value of the function is when you plug 5 in. So let's just go to Desmos and I want to show you this graph. Okay, so here's our graph, x squared plus 2x minus 3. And the question says, what is the limit of the function as the x values get closer and closer to x equals 5? Right? So we're looking for a limit. Well, it just so happens that because this is a continuous function, there's no restrictions, there's no gaps, that all you do is you look at x equals 5 and you go up to the graph and you say, okay, well, it's coming towards a certain y value here and it's coming towards a certain y value here. This is a continuous function, there's no gaps, and so really that limit as x approaches 5 is going to be y equals what? 32. Okay? So the limit here, it does exist, and it actually is the same as if you had just plugged 5 in. So let's just jot some notes down there. Okay? Because this function is continuous, that means there's no gaps, jumps, or asymptotes. Okay, no restricted values here. It's just a polynomial function. The limit of f of x is the same as if you just plugged x equals 5 in. So you have to check that out first. That's actually the first thing you want to do. Just plug x equals 5 in there. For most continuous polynomial functions, that's going to be your limit. If you find that the answer is undefined when you plug it in, then you have to look at the graph or you have to look a little more closely. So really, all you do is the limit here. So the limit equals 5 squared plus 2 times 5 minus 3. The limit is 32. And of course, that is reflected when you have the graph there. If you have 5, this point right here was 32. The point 5, 32. Okay? So a lot of times in calculus, there's going to be some restrictions, right? It's going to be like there's going to be a gap or there's going to be something, and that's what they're asking you to take a look at. But sometimes the default, you want to check first of all. So they use the properties of limits to break it down, but don't worry about it. Okay. So one more thing here. Let's do another example, and that is going to be from your text here. It's going to be example 4. Did I pass it? No, example 4. Okay. So example 4, if you look in your text, it says this: evaluate this. And we're going to read that, of course, as, oops, there's next day's notes. Add some space. Okay, so evaluate this. Let's find the limit of this. So the limit of, this is the function, x squared minus 16 over x minus 4 as x approaches 4. So this is a typical kind of question you're going to get. Okay? And now you notice right away that if I plug x equals 4 into this, I have a problem, right? I'm dividing them by 0. Right? So that's not good. You actually get 0 divided by 0. That's not good. You can't just plug it in and figure it out algebraically. So it would be interesting to know what this graph looks like. And you can just graph it, but you also need to know how to kind of, like what this graph would look like before you just graphed it. So if we factor the top, it's a difference of squares, right? So it actually turns into this. And we can divide out this fraction. And because that, sorry, not the fraction, the factor. Because this is a common factor and it includes one of the restrictions, that means there's going to be a gap discontinuity, right? Or a, gap discontinuity. And so the graph is actually going to look like y equals x plus 4. It's going to look like this line, but it's going to have a gap at x equals 4. Okay? So this is what it's going to look like right here. So x plus 4, we have 1, 2, 3, 4, and we have a slope of 1. So it's going to look like that, but at x equals positive 4, right here, there's going to be a gap. And so you would do a better job than I just did there of showing that. So let me just erase that. So it looks like this, and then at 4, it's going to be an open hole. Okay? Does everyone see that? So what is the limit as x approaches 4? So don't look at this space, but look at the graph around it. You know, what would it be? Well, if the graph looks like this line, what if you tried to put x equals 4 in there now? What would you get? You get y equals 8. So, does it make sense that this is 8 right here? Yeah. So, there's our next lesson. Algebraically, if you want to find this limit, what you do is you factor the top, the numerator, and factor the denominator. Divide out any common factors just like you did in pre-calculus 30. Simplify it, then plug your value in, x equals 4. Then try it. And that is probably going to be your limit there. Okay? So what are the steps? Factor, numerator, and denominator. Divide out common factors. Plug the x value into that expression. And that's going to equal your L. Then, of course, you might want to confirm by graphing. Just to make sure that that is, in fact, the case. So I'll let you get this down here, and then we'll graph it together. Okay, so I've used Desmos this lesson, but why don't we use the graphing calculator here, because you all have the graphing calculator in front of you. Most of you here, all of you in this classroom. Anyways, so how would we do this? Well, let's go to the y equals. Let's clear that out. And then let's plug this in. So use your brackets. X squared minus 16 bracket divided by, use your bracket again, x minus 4. And then we want to graph that. So there you go. It looks like y equals x plus 4. Okay? And now here's something interesting. If we wanted to calculate a value, and I put in 7.99 in there. Why did I do that? I'm not sure. I was thinking of something different. Okay. Not 7.99. Let's do 3.99. That's what I meant to do. Thank you. Oh, 3.999. What do we get? We get 7.999. So do you see how it's close to 4? Now if I tried 4, look what it does. Da, da, da. Because it's not defined there. There's a gap. So when you graph, you can double check what you're doing algebraically, and you can plug in a value that's really close. Okay? I'm going to need you to actually do this algebra to show me, that you know what you're doing. But of course, you can graph it to confirm, what you're doing anytime. Okay? Questions?